Can you believe it? About 85% of the matter in the universe is something we can't see. It doesn't emit light, reflect it, or even absorb it the way everything familiar around us does. Yet it's everywhere, like an invisible hand pulling the strings that shapes galaxies, galaxy clusters, and the vast cosmic web. That mystery is called dark matter. Dark matter is not darkness. Darkness is merely the absence of light. Dark matter, if it truly is matter, is a form of existence that does not interact with light in the usual way. In other words, telescopes that rely on light are almost powerless against it. We don't see it, but we do see its gravitational effects on things we can see. Imagine you are watching a race. According to familiar physics, a race car that's farther from the center of a curve must slow down to avoid flying off the track. In galaxies, however, the car's stars at the outskirts do not slow down as predicted. It's as if there were a heavy, invisible wall around the track holding them in. That wall is the hidden mass, the first clue that there is more than meets the eye. Not only that, when light from distant galaxies passes by a massive clump of matter, it gets bent like a magnifying glass, bending rays of light. This effect is called gravitational lensing, and many times the bending is far stronger than what we can account for with the visible matter we tally up. Where does the missing mass come from? Once again, the provisional answer is dark matter. If you ask, maybe we're misunderstanding gravity? That's a fair question. Science is always ready to rewrite the rules when the evidence is strong enough. Yet multiple, independent puzzle pieces, from the way the newborn universe rang and left traces in the cosmic microwave background, to the way galaxy clusters collide, converge on the same conclusion. There is a vast amount of non-luminous mass shaping the universe. So what is dark matter? Is it a new particle beyond the standard model? Huge dark objects drifting in space? Or a super-light field spread smoothly across the cosmos? Each hypothesis opens a different door into new physics where there may be particles, forces, even principles we've never touched before. And the bigger question, why should we care? Because if we understand dark matter correctly, we can decode the architecture of the universe, why galaxies form, why the cosmic web is woven like giant filaments, and where the far future of the universe is headed. By physical intuition, the farther from the center of gravity, the more stars should slow down, just as planets farther from the sun orbit more slowly than Earth. But observations of hundreds of galaxies show an almost flat rotation curve. Stars on the outskirts do not slow down as predicted. It's as if a massive, invisible halo surrounds the stellar disk and holds the stars in. That halo, if it does not shine, is the first fingerprint of dark matter. The second clue comes from gravitational lensing, the bending of light by mass. Sometimes the effect is strong, forming rings or multiple images of the same distant galaxy. Sometimes it's just a subtle distortion in the shapes of tens of thousands of background galaxies, barely noticeable to the eye. From that tiny shear, astronomers can reconstruct a mass map of space. And the odd result repeats again and again. The mass inferred from light bending is much larger than the total from stars, gas, and dust we can count. Where does that gap come from, if not from a non-luminous, gravitationally dominant component? When two galaxy clusters barrel through each other at tremendous speeds, the scene is even clearer. The hot gas between them collides violently and glows in X-rays. The galaxies, like pebbles, mostly pass through one another with little hindrance. And the mass map from gravitational lensing shows the main mass peaks do not sit with the hot, colliding gas, which interacts strongly, but follow the galaxies, which interact weakly. In the famous bullet cluster, this picture is razor sharp. Most of the mass there is non-collisional, nearly passing through just what we expect for cold, weakly interacting dark matter. This is a crime scene that is hard to explain by tweaking gravity alone. Look farther out, and we meet the cosmic microwave background, the baby picture of the universe at about 380,000 years old. The sky is mottled with tiny temperature ripples, but the notes in their acoustic spectrum require a non-luminous mass component to fit the data. Baryons are only a small fraction. Most is dark matter, and there is also dark energy. Remarkably, the ratios inferred from that baby picture match what we see in today's large-scale structure, as if the universe has been telling a consistent story from birth to now. Over time, those tiny ripples are amplified by gravity, weaving a filamentary cosmic web, strands connected to nodes where galaxies and clusters pile up. When cold dark matter is included in numerical simulations, the web's geometry and statistics naturally come out very close to what deep surveys observe. Remove dark matter, and galaxies struggle to form fast enough to match the sky's story. In other words, dark matter isn't just sufficient to explain one isolated phenomenon. It's the piece that ties together many puzzles that used to look unrelated. Put it all together: galaxy rotation curves, gravitational lensing, cluster collisions like the bullet cluster, and the CMB plus the cosmic web, and we hear the same story. There is a non-luminous mass component dominating the matter budget of the universe, not emitting light, interacting only weakly beyond gravity, arranged in halos around galaxies, and linked by giant filaments on cosmic scales. If the footprints are this clear, who left them? In the next part, we'll open the suspect files, from weakly interacting massive particles to ultralight axions and even dark astrophysical objects, to see who best fits the shadow pulling the universe's strings. We've seen compelling footprints. Now it's time to open the suspect files to see who dark matter could be. First up, the most famous, WIMPs, weakly interacting massive particles. Their appeal lies in the thermal miracle. If the early universe was a thick particle soup, where particles were constantly being created and annihilated, then a particle with mass around the electroweak scale and interactions of about weak strength would freeze out as the universe expanded and cooled, leaving roughly the present dark matter density. It's a neat, elegant picture. WIMPs also arise naturally in many extensions of the standard model. Their signatures would be ultra-faint knocks on nuclei in deep underground detectors, annihilation products such as gamma rays or positrons from regions rich in dark matter, and in colliders, missing energy like an invisible footprint. The trouble is that after decades, there's no definitive detection. Null results haven't killed WIMPs, but they have squeezed them into narrower parameter corners, forcing us to think more subtly about their mass, interaction types, and even their cosmological history. Second, axions, ultralight particles born from attempts to solve the strong CP problem in QCD. Why a term that would violate CP seems essentially absent. The Pesce-Quinn mechanism turns that thorny question into the appearance of a new particle. If it permeates the universe, the action could be dark matter. Unlike billiard ball WIMPs, ultralight axions behave like a smooth field with wave-like properties, potentially softening small-scale structure and producing chord, not cuspy, centers in dwarf galaxies. The axion's telltale is its ability to convert into photons in strong magnetic fields. Resonant microwave experiments listen for an exceedingly faint tone at the right frequency. Solar axion helioscopes look for converted photons, and light shining through walls setups probe photon-axion-photon conversions. Some astrophysical hints like stellar cooling rates point to interesting regions, but conclusions remain open. A broader branch is dark sector dark matter, not a single particle, but an entire family that barely interacts with us, yet may interact among themselves as their own self-interacting dark matter. A touch of self-interaction can help with small-scale puzzles, such as why many dwarf galaxies appear to have soft cores rather than sharp cusps, or why the predicted number of big satellites seems higher than observed. The signatures are subtler, encoded in halo shapes and dynamics, in cluster collisions, and in the statistics of the cosmic web, morphological measurements of the big picture. Then there are the astrophysical candidates, collectively machos, massive compact halo objects, like brown dwarfs, faint stars, or non-emitting black holes. The classical idea was tempting. Maybe the halo is a sea of dim objects we haven't counted. But micro-lensing surveys, watching for the characteristic twinkle as a dark object passes in front of a star, have ruled out machos as the bulk of the halo over many mass ranges. A modern twist: primordial black holes formed very early from dense fluctuations was revived after gravitational wave discoveries. Some mass windows remain, but they are tightly constrained by micro-lensing, early universe heating effects, and delicate stellar dynamics. Signatures here include black hole merger statistics, microlensing of very distant sources, even FRBs, and heating of fragile star streams. There are also fringe suspects, sterile neutrinos at KeV masses acting as warm dark matter that smooths small-scale structure, or particles with dark charge that interact via a dark photon. Each scenario brings its own fingerprints: a narrow X-ray line, a subtle shift in the satellite population, or a missing energy signal in beam experiments. No suspect is perfect, but the fact that the empty spaces are shrinking is the good news. It forces better methods, opens paths to new physics, and sharpens our picture of how the universe builds itself. WIMPs are mentioned most because the picture is beautiful. A heavy, weakly interacting particle abundant in the young universe that freezes out to just the right amount. But that beauty is being tested. A suite of underground experiments has not seen the delicate nuclear recoils WIMPs were expected to cause. Telescopes haven't found unambiguous annihilation signals from dark matter-dense regions. That doesn't rule WIMPs out, but pushes them into more nuanced scenarios, much lighter or much heavier masses than first guessed, non-standard couplings to nuclei, or living in a hidden sector we can only touch indirectly. If WIMPs are the culprit, confirmation would come from a recoil spectrum of the right shape, a missing energy signature in high-energy collisions, or a characteristic gamma-ray line from self-annihilation. Axions appeal in a different way. They solve an old particle physics riddle, why the strong force scarcely violates CP, and could simultaneously solve dark matter. Canonical axions are extremely light, so they act more like a pervasive field than a stream of discrete particles. At ultralight masses, their wave nature can soften the cores of dwarf galaxies, matching some observations of not too cuspy central densities. Their hallmark conversion into photons and strong magnetic fields motivates exquisitely sensitive, radio-like receivers tuned to a specific frequency, solar axion searches, and light-through-walls experiments. A few astrophysical hints like anomalous stellar cooling make the story enticing, but decisive evidence is still missing. Beyond the two headline candidates, the landscape broadens. The dark sector could host an ensemble of particles that barely talk to us, but talk to each other. A smidge of self-interaction might explain core cusp tensions and satellite counts. The trail here doesn't blaze as a bright line. It hides in halo geometry, satellite distributions, and small offsets in cluster collisions. It asks us to read the fine print on the universe's grand image. Astrophysical candidates grouped as machos once looked promising: brown dwarfs, stellar remnants, compact dark objects filling halos. But microlensing has erased most of that possibility. Primordial black holes born from early overdensities got a second wind with gravitational wave detections. Even so, they face tight bounds from microlensing, early universe constraints, and fragile stellar systems. The cautious verdict: they might contribute, but it's hard for them to be everything. Another name is KeV-scale sterile neutrinos, warm dark matter. They smooth structure on small scales and earn some points, but face pressure from the Lyman alpha forest and potential faint X-ray lines. Add to that dark photons, millicharged particles, the ingredients of a tiny bridge between our world and the dark one. Each scenario lays down a different signature: a razor-thin X-ray line, a minute shift in satellite statistics, a missing energy blip in beam experiments. What all suspects share, none is flawless, but each sharpens our tools and our questions. As parameter boxes turn gray after each null result, that's not failure, it's the map coming into focus. We learn where not to look, so we can pour effort where hope is higher. And if a real signature appears, a recoil with the right shape, a line at the right energy, a halo geometry that can't be faked, both particle physics and cosmology will turn the page to a new chapter. Across the world, hundreds of scientists are hunting the cosmic shadow along three main paths: catching it directly underground, eavesdropping on indirect traces in the sky, and producing it in particle colliders. Each path is a net with different mesh. Together they cast into the invisible ocean, hoping to haul up a decisive clue. The first path is catching in the act. Place ultra-clean targets, liquid xenon, liquid argon, ultra-pure germanium deep under mountains, far from background radiation, and wait for the faintest tap. If a dark matter particle, say a WIMP, passes through and hits a nucleus, it leaves a tiny flash, a ripple of charge, or a whisper of heat. From xenon and LZ to Pandex and Super CDMS, these experiments have patiently accumulated years of data, driven backgrounds down, and probed ever deeper parameter space. So far, there's no community-accepted hit. But that's not an empty result. Every "not here" draws a new boundary on the map, crossing off mass coupling combinations once thought plausible. Gradually, if WIMPs exist, their portrait is becoming clearer. They must be lighter, heavier, or stranger in how they interact. The second path is listening for echoes. If dark matter annihilates or decays, the product's gamma rays, positrons, neutrinos could betray it. Space and ground-based observatories from Fermi-LAT to HESS and MAGIC watch the galactic center, dark matter-rich dwarf galaxies, and faint gas clouds for distinctive spectral features. On the ISS, instruments like AMS-02 count cosmic rays, hoping to spot a small deviation from the natural background. The current picture is cautious. Several tantalizing glows have faded as data improved. With traditional astrophysics pulsars, shock acceleration and supernova remnants offering cleaner explanations. That doesn't kill the hunt. It forces tighter targeting, better modeling of the sky's noise, and cross-checks across channels so we don't miss a dark corner. The third path is naming it in the lab. At the LHC and other colliders, when two protons smash together, energy can turn into new particles. If a dark particle is born, it slips out like a ghost, leaving behind missing energy momentum. Monophoton, monojet, and invisible Higgs decay searches are examples. To date, there's no conclusive discovery, but the limits are steadily tightening. If the culprit lives near the electroweak scale, it hides more cleverly than we first thought. Alongside those three pillars is an entire craft guild dedicated to axions and ultralight cousins. Instead of waiting for a nuclear knock, scientists listen for the right microwave frequency. In a strong magnetic field, axions can convert into photons. ADMX, Haystack, and designs like Mad Max are widening the scan band bit by bit, like turning a radio dial to find an ultra-weak station. In another approach, axion helioscopes like CAST look for solar axions, while light shining through walls tests see whether light can vanish and reappear after passing a magnetized barrier. Each no-show slices away a narrow strip of parameter space, and sometimes clues come from astrophysics, stellar cooling rates, white dwarf pulsations, or even the propagation of gravitational waves through a dark medium can set delicate bounds on axions. There are also reading the picture strategies, measuring halo shapes, counting faint satellites, analyzing how clusters pass through each other, or mapping the cosmic web down to small scales to detect dark sector self-interactions. This is the spear point of the interacting dark sector. If dark particles push-pull on one another, halo geometry and stellar motions at the edges will reveal it. No single machine can do it all. There's only an orchestra, each instrument playing its part. In short, not yet seen isn't standing still. It's quiet progress. The suspect map is less fuzzy, the instruments better, the hypotheses sharper. If the day comes a recoil of the right shape, a line at the right frequency, missing energy in a way that can't be denied, we won't just put a name to the shadow. We'll fling open a door to a new slice of physics. If we zoom out, dark matter's importance lies in how it forces us to refine foundational questions. For example, when we chart the universe's structure growth history across time, any small deviation from predictions is a clue. Perhaps dark matter self-interacts slightly, softening dwarf galaxy cores. Or perhaps it's an ultralight field leaving tiny oscillatory fingerprints in stellar motions on galactic outskirts. These aren't just labels for the culprit. They reset the standards for future cosmological measurements, from how we calibrate standard candles to how we meld microwave background data with deep galaxy surveys. Closer to home, the hunt is a test of scientific temperament. We may not see the thing we first hoped for, but every new boundary that says not here turns a tangled ignorance into a structured map, and that map guides us more accurately. That's why null results are still celebrated. They free resources from dead ends, open doors to fresh ideas, and draw particle physicists, astronomers, and measurement technologists together. If one day the change the law, not the stuff scenario wins, meaning gravity needs modification in some regime, the prize is still huge. We would have a deeper principle explaining motions from single stars to whole clusters. Conversely, if we identify the particle nature of dark matter, the treasure is even bigger. Behind one particle might lie a whole dark sector with forces, millicharged particles, even condensation and phase transitions. In other words, a universe within the universe with its own chemistry and meteorology. Don't forget the technological spillovers: ultra-pure liquid xenon vats, calorimeters operating near absolute zero, quantum-limited amplifiers. These don't vanish when experiments end. They flow into biomedicine, geophysics, environmental sensing, secure communications. Sometimes a small improvement in detecting a breath-soft signal becomes a big leap for early diagnosis or infrastructure monitoring. Basic science is, in a sense, civilization's long-horizon R&D. On a very human level, dark matter is a gentle reminder to stay intellectually humble. What dazzles the eye isn't always what matters most. We need tools that look beyond the light, literally and metaphorically, to understand complex systems around us. That's a virtue worth carrying into classrooms, meeting rooms, and everyday life. Don't rush to conclude from what's easy to see. Look for the hidden structure that governs how things work. So what's the ending picture of this episode? Dark matter, whether a particle or a tweak of the law, acts as the universe's scaffolding. Pin down its nature, and we cement another cornerstone in our edifice of understanding. Why galaxies form, why the cosmic web is woven, and why the far future has the shape it does. For now, every tighter limit and every more precise measurement is a firm step along that path. If you've come this far, pick a suspect and a hunting method you find most convincing. Do you lean toward WIMPs with their underground xenon vats, or axions with microwave radios tuned to a particle's private frequency? Or do you want to bet on subtle geometric fingerprints in halos in the cosmic web? In the next episode of this series, we can dive into your choice, why it's compelling, which experiments are running, what milestones may bring answers in 3-5 years, and if not yet, what the next step should be. The universe's key is right here in patience, precision, and the courage to doubt our way forward. We already have the lay of the land, evidence from rotation curves, lensing in the CMB, suspects from WIMPs and axions to a whole dark sector, and 3 fronts: underground, sky, and collider. The practical questions now are, what might happen in the next few years? How will we know a discovery is real? And if it's not yet, how do we proceed? First, the gold standard for discovery. A signal must rise well above background, be repeatable, and ideally appear in multiple ways. A hit in xenon becomes truly convincing if it lines up with a glow in the sky or a missing energy signature in a detector. The universe doesn't reward coincidences, it rewards a coherent picture. Ahead lie 3 doors that could swing open at any time. Door 1, direct detection. As purification and background suppression advance, sensitivities will reach smaller and smaller interaction strengths. If events appear with the right recoil shapes, time dependence, and model expectations in multiple groups confirm them, that will be the moment to name a WIMP-like or other feebly interacting culprit. Door 2, indirect listening. A narrow gamma-ray line at just the right energy that persists across multiple dark matter-rich sky regions, like dwarf galaxies, and can't be blamed on known astrophysical sources would be a heavyweight signature. For axions and ultralight particles, the signature is a frequency. When a microwave radio scans wide and catches a back-and-forth tone at the predicted frequency that stays stable over time, that's a serious candidate. Add a cross-check from an axion helioscope or a light-through-walls test, and suspicion hardens into belief. Door 3. Production in colliders. If several analyses show a repeating pattern of missing energy momentum, tied to invisible decay channels, and consistent with a minimal model, for example, a dark portal, coupled to the Higgs, that would be laboratory-grade evidence that the dark sector is real. In a parallel, observational astronomy will pave the way. Deeper, wider images to read halo geometry, count faint satellites, and track cluster pass-throughs to test for gentle self-interaction in the dark sector. Tiny numbers of small shear, a small velocity offset when amassed across the sky, can tip the scales between models. If a decisive signature arrives, the next step isn't just to announce it, it's to measure properties. What mass? What interaction? How does it evolve across cosmic time? The answers feed back into simulations, updating how galaxies grow, how the web is woven, and even the universe's expansion clock. If the culprit is an axion, we open a new drawer in nature's cabinet. Other ultralight species, dark photons, hidden symmetries. If it's a WIMP or kin, ties to the electro-weak sector and the Higgs become the bridge between particle physics and modern cosmology. If clues favor self-interaction, we will read halo shapes and stellar dynamics like fingerprints. And if it's still not yet, that's not a full stop, but a pivot. We'll look to much lighter or much heavier masses than already explored, to non-standard interactions, say, favoring electrons over nuclei, or to change the law pictures in some gravitational regime. Each crisp null result is a rung that lifts us from vague speculation toward a structured view. As our companion through the series, you play a key role. Keep the questions sharp and choose a direction to dig. Do you want a full episode on WIMPs, why the thermal miracle once captivated the field, and what room WIMPs still have? Or do you want to listen for axions particles so light they behave like an ocean, and the odd radios we must build to hear them? Or would you rather explore how a dark sector, if it exists, reshapes halo geometry and stellar motions?